In this chapter, we're going to look at the graphs of polynomial functions and especially at their behavior for x going towards plus and minus infinity and at zeros. Let us start with the behavior at infinity. The behavior of such a polynomial function here at infinity is determined by the leading term an x to the power of n. Let us look at this example here to understand why this is the case. So the leading term is 3x to the power of 5. We rewrite the polynomial by factoring x to the power of 5 out of the expression, so we get x to the power of 5 times this bracket. Now, when x goes towards plus or minus infinity, then this whole expression here goes towards 3, since all of this here goes to 0. And so we get as an approximation that p of x is x to the power of 5 times 3 when x becomes really large. So this means that we only have to look at the behavior of the leading term to understand the behavior of the whole polynomial when x becomes plus or minus infinity. Well, this behavior depends on whether the n here is even or odd and whether the an here is positive or negative. Let us visualize this behavior by filling in this table here. Here we have the n, so either it is even or odd. Then we look at the an being positive or negative, so we have it here, an positive and here an negative. And now let's look what happens with the value of the polynomial. For example, in this case here, when x goes to plus infinity, n is even and an is larger than 0. Well, think for a moment. Well, the result is plus infinity. What happens if x goes to minus infinity? The result is again plus infinity. Why is this the case? Since an is larger than 0, we have here something positive. N is even, so a negative number here, x, to the power of something even will be positive. So we have positive times positive, and the x itself becomes infinitely large. So the whole thing goes to plus infinity. So looking at the behavior when x goes to plus infinity, it means going in that direction. Looking at the behavior when x goes to minus infinity, we're going that direction. And we said in both cases, the whole thing goes somehow off to plus infinity. So it'll look something like this. Fill in the rest of the table by your own. Just first you can fill in to where the polynomial function of x goes towards and watch what the result is. Then in the second step, sketch the corresponding graph parts. So stop the film now. Here comes the result for the first part. So this is toward infinity. P of x goes towards, and now let's look what this means for the graphs. And here is the result. So we have both ends going towards plus infinity or both ends going towards minus infinity. That is, if the n is even. If the n is odd, one end goes to minus infinity and the other one goes to plus infinity. Next, let us look at behaviors at zeros. We have learned that we can write a polynomial always as a product of linear and non-factorizable quadratic polynomials. So let us look, for example, at this polynomial here already factorized. Its graph is shown here on the right. And let us now look at the behavior of the polynomial function when the x value is close to 3. When we look at the different terms of this product, we see that actually it makes a huge difference in this term here, whether x is just a tiny little bit larger than 3, little bit lower than 3, or just when changing it a little bit and you're close to 3, here you have quite some impact. However, here, when you're close to 3, this will be always approximately 1. This will be always approximately 4, so 3 minus 1 to the power of 2, we get 2 to the power of 2. Or here, when we're close to 3, we have approximately 10. And that's the idea now, to have an idea what happens when x is close to 3. We just insert everywhere here for the x a 3. And we get then in the end that the polynomial can approximate it as 40 times x minus 3 to the power of 3 when we're very close to x equals 3, so here around. Well, we know how this looks like. We looked at that before in the chapter 1.2. We know it is this S shape. We can now apply the same idea to the other zeros. So here we have a 0 at x equals 2. So again, we insert now for all the rest x equals 2. So we will get something times x minus 2. Well, this means we get a straight line. This something, when we insert everything in here, we find that it is minus 5. So minus 5 times x minus 2. This means we have a descending line, like here. For x equals 1, the next 0, again inserting 1 everywhere here, we get that it is 16. So we get 16 times x minus 1 squared. So we have a parabola with a positive an. This means we get a U shape facing upwards. We can now generalize our findings. If we have a single 0, this means the 0 has the exponent 1 here. It's a linear factor. So we'll get a straight line here approximately. If it is a double 0, like here, or a 0 with the power 4 or 6, so with a even multiplicity, then we know we'll get a U shape, this or this. If the multiplicity of the 0 is 3 or 5 or 7, so odd and larger than 1, then we know we'll get an S shape like this or like this. So let's write down our findings. If we have a single 0, a simple 0, then the graph just cuts the x-axis. If the multiplicity of the 0 is even, so it's to the power of 2, to the power of 4 or so, then we know the graph touches the x-axis. And if the multiplicity is odd and larger than 1, for example 3, so a triple 0 or 5, 7, so the graph cuts the x-axis horizontally. Let us now look at some examples. In example 1, we want to discuss the graph of this function. We find here also its factorization. So let's start with its behavior for going towards infinity. So when x goes to minus infinity, we have an even exponent. So what will happen? Minus something large to something even, we'll get plus something large. This is positive, so it goes to plus infinity. What happens when x goes to plus infinity? Well, obviously, the whole thing goes also to plus infinity, and that's what we see here. We go off to plus infinity when we go to the right or to the left towards infinity. Let's then watch the zeros. Well, the 3x equals 3 is this 0. That's a single 0. So at 3, the graph just cuts the x-axis. X equals 1 is a triple 0. Here, the 3 for x equals 1. So we have an odd multiplicity larger than 1, so we get the S shape as we see it here. And for x equals minus 2, here we have an even multiplicity, a double 0. So the graph touches the x-axis. So if we had to sketch the graph by our own, we would say, well, starting for x being at minus infinity, somewhere here, we see we come from plus infinity, so we come from up, down. Then the first 0 that we meet is here at minus 2, and we have to touch the x-axis, so somehow we go up, whatever happens then. And then the next point that we know about is here the 1, where we have to cut the x-axis horizontally. So we went up here, so we have to get somehow down here and go further down here. The next point we know is at 3, we have to cut the x-axis again, so we have to turn back and go up, and then we go off to plus infinity, so everything works fine. So in example 2 now, let's sketch the graph by our own. In order to find the behavior at infinity, let's find the leading term. The leading coefficient is just -2. And what is the highest occurring power of x? Well, here we'll get x to the power of 4, here x to the power of 5, and here x to the power of 6. And multiplying it means just adding these exponents. So we get in the end -2x to the power of 15, plus then some other terms that we're not interested in. And now we can start. So proceed now in the same way as up here, and then sketch the graph. Do that on your own. Stop the film now, and here comes the result. So for x going to -infinity, the p of x goes to +infinity, x to the power of 15 goes to -infinity, since we have an odd exponent, the minus remains, and times a negative coefficient, it becomes plus, so it goes to +infinity. When x goes to +infinity, this stays positive, but times a negative number, it goes off to -infinity. Then we have 5 zeros, a 0 at x equals 5. This is a 0 with an even multiplicity, so we call it an even 0. At x equals -2, we have an odd multiplicity, so we call it an odd 0. And at x equals 3, we have again an even multiplicity, so an even 0, which means at 5 we touch the x-axis, at x equals -2 we cut it horizontally, and at x equals 3 the graph touches it again. So now we can draw the graph. So we start somewhere at infinity here, then we cut horizontally at -2, and we touch twice, namely at 3 and at 5. So we'll get something like this here. And yes, we see now we went off to -infinity as predicted here. So this is sort of a control. If we had got here +infinity and we went off here to -infinity, we would know that something was wrong, either in the way that we found the behavior at infinity or for the zeros. Now try the example 3 on your own. Stop the film, and here comes the result. For the leading term, the leading coefficient is just the 100th here, and to find the exponent, we have to look here again. We have 2, 1, 3, 4, and here is just squared, so 2. So adding 2 plus 1 plus 3 plus 4 plus 2, we get 12. So we have an even exponent here, and the coefficient is positive, so we know the shape is like this. So it goes off to +infinity for x going to -infinity and for x going to +infinity. For x equals 2, we have an even 0, namely a double 1. The same is for x equals 3. We have also an even 0, 4 times 1. For x equals -1, we have a single 0, which means there the graph just cuts the x-axis. For the other ones, for the even ones, before it touches them. And then we have x equals 5 as the last 0. It's a triple 1, so there the graph cuts the x-axis horizontally. So for x being negative, we start somewhere at infinity, so up here, and then the first 0 is at -1. We cut just somehow. Then at 2 and at 3, we touch the x-axis, and at 5, we cut it horizontally. So it has to look something like this here, then going up and cutting horizontally. And we see we go off to +infinity here, which corresponds to what we found here. So everything looks all right. Due to the fundamental theorem of algebra, we know how many zeros a polynomial of degree n can have at maximum. Since we can factorize it at maximum into n linear factors, this means it can have at the maximum n zeros, whereby we count multiple zeros with their multiplicity. Now, how much is the number of possible zeros at all? Well, it is n minus 2k, k being some natural number, which means For example, if I have a polynomial of degree 7, I cannot have 6 zeros, all the time counting zeros with their multiplicity, because I can't have 6 linear factors only. I can have 5 linear factors and 1 quadratic, or then I have 7 linear factors. That's the reason why I will always have either the maximum of the possible zeros, so the n, or then just a multiple of 2 less than the maximum. So study example 4, decide on your own which of the statements can be true, which not. Stop the film, and here comes the result. A is true because the difference between 5 and 7 is 2, a multiple of 2. B is wrong because the difference between 2 and 7 is 5, which is not a multiple of 2. C is wrong because this means that there are in total 11 zeros. Well, we know at maximum there could be 7 zeros. And D is correct because here the zeros are not counted with their multiplicity. It just says 6 distinct zeros. So this means there are 6 distinct zeros, 5 of them are single ones, and 1 is a double one. Now let us look at example 5. Here you're given the equation of a polynomial function of degree 3, and you're not given its factorization. So what you have to do is to guess one of the zeros first, and then using polynomial division, you can find the other 2 zeros, and then you can sketch it. So go ahead, solve it on your own, stop the film, and here comes the solution. We start with the guess x1 equals 1, and inserting it here we find really the result is 0, so we are successful. We found a first zero, x1 equals 1. The next step is to divide the polynomial by the linear factor that we found with the help of the 0, namely x minus 1. And we get in the end minus x squared plus 1/2 x plus 13 divided by 2. So we have now to set this equal to 0. Let's multiply it by minus 2. We get this equation here. Trying some systematic guessing, we'll find out very quickly, well, there is no simple solution, so we have to use the midnight formula, and we find this expression for the 2 solutions. So we get the 2 solutions, 2.8 and minus 2.3. And so we have found 3 single zeros, namely at x equals 1, x equals 2.8, and x equals minus 2.3. Now let us also look at the behavior at infinity. The leading term of the polynomial is minus x to the power of 3. So when x goes off to minus infinity to the power of 3, it stays minus. We have a minus in front, so it becomes positive. So the polynomial goes off to plus infinity. When x goes to plus infinity, x to the power of 3 is plus, minus in front, it becomes minus infinity. So now we can sketch the graph. We have the zeros at 1 and at 2.8 and at minus 2.3. For x going towards minus infinity, p of x goes to plus infinity, so we come from somewhere up here. We cut the x-axis, we have to cut it again here, and we have to cut it once more. And we see the behavior seems to be correct, since for x going towards plus infinity, we go towards minus infinity, as found here. We have sketched the graph of our polynomial just based on the behavior at infinity and on the zeros. What 2 points would be most helpful to know to improve this sketch? Think about it for a moment. Stop the film. Well, I think it should become clear that the most important points would be these 2 turning points, or we call these also the local minimum and the local maximum, so the local extrema. Their coordinates are 2, 3.5 and minus 1, minus 10, and we will learn very soon how to find these coordinates, these points, when we start with differentiation. You can use these points now to improve your sketch. For the last two examples, we invert the question. Until now, we were given the equation of a polynomial function and we wanted to sketch the graph. Now we're given the graph of the polynomial function and we want to find its equation. In example 6, we're given that a polynomial is of degree 4, quartic, and this is its graph, so let's find its equation. The idea is to use the 3 zeros here to find the ansatz and then use the point here given, the y-intercept, to find the last remaining parameter. Do it on your own, stop the film, and here comes the result. Using the 3 zeros, we find this ansatz here, y equals a times, that's the one thing that we don't know, and then using the zeros, so minus 2 yields x plus 2 is a single zero, then 1 yields the factor x minus 1, it's touching here, so it has to be x minus 1 squared, and the third zero here, 3, is x minus 3, again a single zero, that's why we get this ansatz. Now let's insert the y-intercept and we get this equation here, since 0 minus 1 squared minus 1 squared is 1 here, and next step, let's find the a by dividing here by minus 6, we find a is equal to 1/4. Now inserting the a into this equation p, we get the final result for our polynomial. In example 7, you have to find the equation of the polynomial given by its graph here. However, contrary to example 6, we're not given the degree of this polynomial. We only know it should be the lowest possible degree. When you have a zero where the x-axis is touched, you know that the multiplicity has to be even of that zero, and since it should be of lowest possible degree, you assume that the multiplicity is just 2. That's the meaning of this lowest possible degree. So find the solution on your own now, stop the film, and here comes the result. The ansatz for our polynomial function equation is y equals a times, so the unknown parameter a. Then we take this 0, so we get x plus 3. It is touching, so we have to take it to the power of 2. Then the next 0 here, we cut horizontally, so we get x plus 1 to the power of 3. And here at 1.5 or 3/2, the graph touches the x-axis, so we get x minus the 3/2 squared. Next, we insert the given point, the y-intercept 0, 27, into this equation. We find this equation here, and then we can just solve it by multiplying with 4 divided by 81 to find a is 3/4, and we get the final equation for our polynomial function.